Thank you. Thank you very much for the invitation. It's really nice to have a chance to give this talk online. And also next week, I'm going to Cambridge and give the same talk over there. So it's really like I try to fix every single detail of the talk before the real conference. Anyway, today I'll talk about something related to the Okounkov bodies. And here you see the adjective partial Okounkov bodies. I will try to explain to you the relation with the Euro Okounkov body and also the relationship with the partial Okounkov bodies and the toric geometry. And there are two main references to this talk. The first one was my paper written like 3 years ago, and the second one was my lecture notes in Zhejiang University, which contains a lot of more information about these partial Okounkov bodies. And in the whole talk, we're going to fix the following notations. We're going to consider a projective variety, and usually we consider only the smooth projective varieties, and we write it by as x. And we're going to fix the holomorphic line bundle on x, and on L, and the line bundle is denoted by L. And on L, we are also going to fix a positively curved metric. That means we're fixing a metric which could take the value 0 at some points. And the only assumption is that the metric has to be positively curved. That means the curvature current is a positive current. In the first part, I'll talk about some backgrounds. First of all, let's make sure that we agree with the definition of the convex bodies, because in the literature, there are several different ways to define them. And in this talk, a convex body always means a non-empty compact convex subset in Rn. And what is the Okounkov body? It is actually something introduced like more than 10 years ago and has been well studied in the literature. Initially, they are introduced by Lazarsfeld and Mustată and Kaveh and Khovanskii based on the works of Okounkov. And the Okounkov bodies, they are not a single convex body, but they are really a family of convex bodies parameterized by some parameter nu here. And I'll explain the parameter later on. And they're associated with the data, the given data of the line bundle L. So like given a line bundle L, you have a canonical family of convex bodies associated with them. But the problem is, why do we study these convex bodies? The idea actually came from toric geometry. As is well known in toric geometry, people can always translate the geometric information into the study of the corresponding convex bodies. And in the non-toric situation, we really want to use these convex bodies, these Okounkov bodies, as a replacement of the convex bodies happening in toric geometry. So the main purpose of the main motivation to study these convex bodies is the following kind of slogan. The Okounkov bodies is an effective way to translate the geometric properties of our given line bundle L to the properties of the convex bodies. And a priori, our manifold, our projective variety X has real dimension 2n, but the convex bodies they have real dimension n. So a priori, the information about the convex bodies should be simpler than the information about the geometry of X and L themselves. And in our talk, the final goal is to construct some similar convex bodies. But now we are given not only a line bundle L, but also a possibly curved singular metric H on L. So we are considering a line bundle L together with H, and we're going to construct a family of convex bodies still parameterized by the same parameter nu. And we're going to construct these convex bodies, and we want that these convex bodies could translate the properties about the pair L and H into the properties of the corresponding convex bodies. And these convex bodies are the so-called partial Okounkov bodies. And here is a general picture illustrating what happens, the relation between the partial Okounkov body and the Okounkov body. So here you see the black polyhedron is the Euro Okounkov body, but inside the black polyhedron there is a smaller part, and that is our partial Okounkov body. And as we will see in the talk, the partial Okounkov bodies is always contained in the corresponding Okounkov body, and they are related in many different ways. All right, let's begin by introducing the parameter nu. recall that in the on the previous page, when we talk about the family of Okounkov bodies, there's always a subindex nu. And on this page, I'm going to talk about the parameter. And the parameter is given by the so-called flag, or more precisely, the admissible flags of subrarities on X. And what do I mean by that? I mean, a flag simply means like a flag on X. That means a family of subrarities, like Y0 contains Y1, Y2, blah, 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 until Yn. And each subrarity, say Y1 has codimension 1, Y2 has codimension 2, etc. So eventually, the final subrarity Yn has codimension n, and that means Yn is a single point. We're fixing such a a datum, and this flag induces in a canonical way evaluation on the function field of our variety X. And in order to illustrate what I mean by this valuation, let's consider the simplest situation. Like in the picture here, we are considering the one-dimensional situation. So in that case, by definition, the flag simply means like choosing a single point inside our variety X. So Y0 is X and Y1 is a single point. And in that case, the corresponding valuation, if you apply nu to a rational function f on X, then that simply means we're taking the order of vanishing of f along the point Y1. And similarly, in higher dimensions, we have very similar things. Like here is a picture in dimension 2. In dimension 2, the fly consists of two different pieces. The first piece is a codimension 1 subrarity. That means a curve in our variety. That is the Y1 in red here. And we also have a codimension 2 piece. That means a single point Y2 inside Y1. And in that case, the valuation explaining the valuation, the general valuation on the function field takes value in Z square. And the first part of the valuation is given by the order of vanishing of f along the subrarity Y1. It's similar to the one-dimensional case. But the second piece becomes different. So what we do is we first consider our rational function f, and we consider its order of vanishing along Y1. And we remove the vanishing part of f along Y1 so that we get some function which can be restricted to Y1. So you see, we are taking f times t times minus nu1 f, where t is the local generator of the local defining function of Y1. And we restrict the rational function to Y1 so that we get a rational function on Y1. And then we can take the order of vanishing of this rational function on Y1 along Y2. And similarly, in higher dimensions, we can always carry out the same construction. So in some sense, the valuation nu of f is a way to characterize how fast our function decays or degenerates along our flag. And more generally, the parameter could take value, could take the more general values, not necessarily coming from the flags, but they only have the parameter nu runs over the set of all valuations from C of X to Zn with similar properties. And now we can begin to talk about the classical construction of Okounkov bodies. We're still fixing the data X and L, and we're also fixing a subindex nu. So eventually we want to construct a convex body delta nu of L. And in order to construct this body, we need to make some very simple assumptions about L. Here, we need to assume that L is big. That means L has many holomorphic sections. And if you don't know the definition, you could simply imagine like L is an ample lamp bundle, etc. And the construction of the convex body consists of 3 steps. The first step is the transformation from the geometric data to some algebraic data, from the geometric data of XL to a ring. So we begin with our X and L. Since L is assumed to be big, that means L has many holomorphic sections. We can consider its ring of sections, the RXL. We're considering the sections of not only L, but also all of the tensor powers of L. And apparently they form a ring, and this is really known as the section ring of XL. And from the section ring to the next step is to pass from the ring to a semigroup. And in this step, we are in need of the valuation nu here. So what do? We begin with our ring RXL and our valuation. and we construct a sub-semigroup of Zn plus 1. So you see here, we are increasing the dimension by 1. And we have a final coordinate corresponding to certain level structure. And as you can see from this definition, there is the set gamma nu L consists of the pairs consisting of nu of S and K. And so here K is some parameter characterizing the level. Like you can, like in the geometric picture, you can imagine K as a vertical coordinate. And for each K, you consider the set of all holomorphic sections of L to the Kth. And then you consider all of these sections, and you can apply our function. You can apply the valuation nu to these sections, and you put all of these valuations together on level K, and you glue all of the different levels together, and in the end, you end up with something contained in Zn plus 1 more dimension. And eventually, there is a very familiar way to pass from a semigroup to a convex body, characterizing the asymptotic behavior of the semigroup. That means we take the convex hull. Here CONV means we take the convex hull. That means the smallest convex cone containing all of these lattice points. We take the convex hull and take the intersection with the level 1. That means the intersection with xn plus 1 equals 1. This kind of, in the end, we end up with the convex body, which is known as the Okounkov body. And if you have never seen this kind of constructions before, this might seem to be a bit abstract. So I'll try to explain things in a very concrete situation in the following example. I'll explain to you how everything works. So we begin. This is a simple example in dimension 1. We consider x to be P1 and L is O1. And in that case, the flag, recall that we need to choose a flag, and the flag does not have many choices. We can only choose a point in the flag. So we fix the point to be 0. And then the corresponding valuation simply means we take a rational function and apply and consider its order of vanishing at the point 0. That's our valuation nu. And in that case, recall that from the previous part, there are 3 steps to construct the Okounkov body. The first step is to pass from the geometric data to a ring. So that means we consider all of the holomorphic sections of OK. But the holomorphic sections of OK, they are nothing but the polynomials in one variable of degree K. So that's something very simple to understand. And the second step means that we want to pass from the ring to a semigroup. And recall that means we fix each level K, and we considered all valuations of the corresponding sections of level K. So for example, on level 1, the corresponding sections of L, that means the sections of O1, there are nothing but the holomorphic sections of O1, and there are nothing but the linear polynomials in a single complex variable. And if you consider corresponding order of vanishing along the point 0, there are only 2 choices. Either it doesn't vanish or it vanishes to the order 1. So you see that there are only 2 points here on level 1. And similarly, on level 2, you have 3 points because the order of vanishing could vary between 0, 1, and 2. And similarly, you can construct the same thing. And eventually, the red points correspond to the semigroup, the gamma nu L on the previous page. Okay. Eventually, we want to, the final step is to pass from the semigroup to a convex body. And the way of doing that is to first take the convex hull of these lattice points, and then take the intersection of n plus 1 equals 1. And that's a very intuitive way of doing things. Here we have the red points. We take their convex hull, so that becomes the blue part, the cone inside the blue lines. And then we take the intersection of this cone, the blue cone, with the level 1. So we end up with the green line here. And by definition, that is the Okounkov body of XL. So as I read here, delta nu L is a closed interval from 0 to 1. And from this picture, you can see very intuitively that the green line, or the Okounkov body, gives you really a way to characterize the asymptotic behaviors of your semigroup when the level tends to infinity. Because for example, asymptotically, the number of points on level K is around K, and that's the same as the volume of the green line. And in general, we expect something similar. We expect that the Okounkov body gives you a way to asymptotically characterize the corresponding semigroup gamma nu L. After explaining the basic definitions of the Okounkov bodies, let me try to explain why they're useful, or why do we ever consider them. So there are two main results in this direction. I mean, initially there are two main results in this direction. The first result was already contained in the original paper of Lazarsfeld and Mustată, which says that these Okounkov bodies, although their definition depends on the corresponding section ring, some algebraic data associated with L, etc., but it turns out that the Okounkov bodies, they depend only on the numerical class of L. That means if you have two different line bundles and they have the same intersection number with all curves, then they have the same Okounkov bodies. And that is not the most standing point of the Okounkov bodies. The most standing point is that there is a reverse. The reverse direction is also true. The reverse is also true. That was the theorem by Joe, which says that if you consider the family of all these Okounkov bodies, I mean, consider the Okounkov bodies for all flags, then this family actually determines the numerical class of L. So put it in a more fancier way, that means the Okounkov bodies, they are universal numerical invariants of the line bundles. By universal, I mean, like, first of all, they're invariants of the numerical invariants of the line bundles. And secondly, due to the theorem of Zhao, basically, if you know these Okounkov bodies, you know every other numerical invariant of L. So in that sense, we say that these are the universal numerical invariants. And as a very simple example of this kind of phenomenon, there is a very well-known, very famous numerical invariant of the line bundle, the so-called volume of the line bundle, which basically characterizes how many sections there are when L tends to how many holomorphic sections there are for Lk when k tends to infinity. And it is well known that this is a numerical invariant, and this numerical invariant can be computed using the Okounkov bodies, and in the following very simple way. The volume of the Okounkov body is nothing but the volume of the line bundle up to 1 over n factorial. Okay, so that's the background part. And in the next part, I can finally begin to talk about something more interesting about the main subject of today, about the partial Okounkov bodies. Before starting, are there any questions so far? Okay, I don't hear anybody, so I assume that I can move on. Okay, at this step, we're going to talk about the Okounkov body. We're going to talk about these partial Okounkov bodies. In order to talk about these partial Okounkov bodies, instead of only considering the line bundle L, we're also going to fix a positive curved singular metric H on our line bundle L. We want to construct some similar convex bodies. There's a new LH containing our convex body, which depends only on the singularities of H. The analogs of the preceding theorems are also true, which is the main result proved in paper 1, which tells you that these Okounkov bodies, these partial Okounkov bodies, delta nu LH, they depend only on the I equivalence class of the singularities of H, and I'll explain what I mean by that slightly later on. And conversely, the family of all Okounkov bodies, all partial Okounkov bodies, they determines the H, our singular metric H, up to I equivalence. And of course, in order to make sense of this theorem, we need to understand what we mean by I equivalence. We consider two different positively curved singular metrics H and H prime on our line bundle L, and we say that they are I equivalent if all their little numbers are equal. If you know what it means, if not, the I equivalence is a way to characterize the equivalence between the singularities H and H prime. That means they tend to minus infinity in roughly the same way, in the sense that most of the information we are interested in are invariant under I equivalence about the singularities. I mean, two singularities are equivalent if and only if their behavior near minus infinity, their behavior near the degeneration locus are roughly the same. And it's actually the somehow the main equivalence relation we are interested in when studying the singularities. But anyway, the theorem tells you that the singularities up to some natural equivalence are completely determined by these partial Okounkov bodies. So similar to the slogan for the Okounkov bodies, here we have a slogan for the partial Okounkov bodies. The partial Okounkov bodies, they are universal invariants of the singularities of our given metric H. I also need to mention that this theorem, although it concerns the singularities of H instead of telling you anything about the line model L, but in fact, our theorem implies both the theorem of Lazarsfeld and Mustată and the theorem of Zhou mentioned previously. Okay, now let's talk about the constructions of these partial Okounkov bodies. Let's begin by recording what we did for the Okounkov bodies without the singular metric H. There are 3 steps in our construction. The first step is from the geometric data of XL to a ring, the second ring. And the second step is from the ring to the semi-group. And here we need to add the information of the valuation or the flag nu. From RXL and nu, we construct the gamma nu L. It's a sub-semi-group of Z to the n+1. And eventually we pass from the semi-group to our convex body using the convex hull construction. But now if we add our singular metric H into the picture, what do we have? We begin with XLH, and we want to similarly construct a ring from the data. But in order to put H into the picture, the most natural way to do is to put it in the following way. We consider the section ring of RXLH. So that means we're considering not all L2 sections, not all sections of L to the kth, but we're considering only those L2 sections of L to the kth. And here L2 means L2 with respect to the given singular metric H to the kth. But here already we have a problem, because here we are imposing some L2 type condition. But you know, in general, the product of 2 L2 functions is only L1. There is no way to guarantee that RXLH is a ring in general. So we are in trouble already. This guy, although we can construct it, it's no longer a ring. But even though it's not a ring, let's try to see what we can get if we still follow the naive approach as we did in the case of Okounkov bodies. We include the information of nu, and we try to construct some semi-group using our information of X, R, X, L, H, and nu. We try to fix every level K, and where K is an integer, and we consider all sections in the corresponding level K. So that means all L2 sections of LK. And we consider all of these valuations, and we put all these valuations together, and we get some object gamma nu LH, which is a bit weird object, since our R is no longer a ring. The corresponding gamma nu will no longer be a semi-group. All right, if it's no longer a semi-group, then what can we do in the third step? Can we still construct our convex body using the convex hull and take the intersection? Let me show you a picture about what goes wrong if our object is no longer a semi-group, and if we try to follow the same approach in the Okounkov bodies case. Let's come back to the picture we already mentioned earlier on. These are the semi-groups constructed from O1 on P1, and I mean the red points. But now, assume that we are adding a single point to the picture, the green point to the picture. Initially, we know that if we consider only the red points, the corresponding convex hull is given by the axis and the dotted line. So the corresponding Okounkov body is from 0 to 1. But now, since we add the green point, that means the corresponding convex hull increase immediately from this small cone to this much larger cone, bounded by the two blue lines. So if we consider the corresponding intersection with the level 1, we end up with something much larger. We end up with this yellow line from 0 to 4, which is something much larger. But the thing is, we really want to construct some convex body which can characterize the asymptotic behavior of our semigroup. So like when the level tends to plus infinity, the semigroup given by the red points and the object given by the red points plus the green points, they're exactly the same when the level tends to plus infinity, because we're only adding a single point on level 1. But we see that their convex hull becomes immediately different, and the intersection or the corresponding convex bodies becomes immediately different. And so if we construct the convex body using the naive way, we end up with the yellow line, which fails to characterize anything useful about the asymptotic behavior of the semigroup or of the right lines, right points plus the green point. So we really need to find a way to get around this kind of difficulties. So here are the magics, some very useful observations. The key observation is that although our RxLH, it is not a ring, but the point is it is not very far away from a ring. And similarly, our gamma nu LH, although it is not a semigroup, it is not very far away from a semigroup. And the following theorem is essentially contained in my 2 joint papers with Tamas Darwas, and which says that gamma nu LH is an almost semigroup. Of course, this is not a common term, so I need to explain what I mean by an almost semigroup. In more concrete terms, gamma nu LH, this weird object, can be approximated by semigroups with respect to some naturally defined pseudometrics. Here, the pseudometrics compares the distance between 2 different objects to different subsets of z to the n plus 1, and is given by considering the number of points on level k, comparing the number of points on level k of S and S prime. So we are taking the number of points of Sk, where Sk means S intersects with x1 equals k. It's the level set of level k. So we are taking the sum of the points of level k of S and S prime, and we minus their intersection. We exclude their intersection, and that gives you a pseudometric. And essentially, the works by Tamas Darwas and myself showed that gamma nu can be approximated by this by semigroups with respect to this given pseudometric. This shouldn't be too surprising in general, because the construction when the curvature current of H is a Kähler current, the approximating sequence is simply given by the Meyer approximation. But to prove that convergence, it is truly a very non-trivial result. And the second part of the magic is that the Okounkov bodies, although they can initially be defined for semigroups using the convex hull construction, but it turns out that it can be continuously extended from semigroups to almost semigroups. In other words, we have a continuous map from the set of almost semigroups to the set of convex bodies in Rn. And here on the set of almost semigroups, we have the pseudometric, so we have a natural non-Hausdorff topology. But on the set of convex bodies, there is a natural topology induced by the Hausdorff metric, compares how far away 2 convex bodies are from each other. And the surprising thing is this map, you can always define this map in a unique way, because the extension is continuous. So there's only one unique way to define it. Okay, now we can begin to put the 2 magics together. What do we get? Oh yeah. Before talking about further information, let me give you an example about this extension of the Okounkov body of almost semigroups. Let's still consider the case, the example on the previous page. We consider the red points plus the green point. Then it's very easy to prove that this guy is actually an almost semigroup, and the corresponding Okounkov body, by definition, if you follow the definition, you can show that it's given by this purple part instead of the yellow line. So you see that the Okounkov body of the almost semigroup gives you exactly the same Okounkov body as the red points. So that's what we want. we already get something which is useful in characterizing the asymptotic behaviors.
Sorry, Mingchen, can I ask something? Like in this example, they coincide, but does this happen always, or it can be similar but not?
It depends. Like for example, if I add finitely many points to a semi-group, then they always coincide. And if you add some sufficiently fewer points, like some points to the order of k to the -1 to the picture, then it's fine.
Okay. Okay.
That means if you add too many points, of course, the things will change. But if you only add a smaller number of of points, everything's fine in general.
Okay.
All right, now we can come back to our construction scheme. We begin with our XLH. We construct some ring-like object. And then from the ring-like object, we construct our semi-group-like object, gamma nu LH. And from a previous theorem, we know that gamma nu LH is always an almost semi-group. And we know how to define the Okounkov body of an almost semi-group. So now everything becomes clear. We can simply define the Okounkov body, the partial Okounkov body of LH as the Okounkov body of the corresponding almost semi-group. And that would be a sub-convex body of delta nu of L. And that's our main definition. In general, the picture looks a bit like this. we have a convex body, the Okounkov body. Although it is not always a polyhedron, it's not very far away from a polyhedron in general. And we have a subpart, the partial Okounkov body, but it behaves rather differently from the Okounkov bodies because it's very far away from being polyhedron. For example, in dimension 2, we have very nice polyhedral structures of the Okounkov bodies, but for the partial Okounkov bodies, it's in general very different. Like you can see some really curvy parts in the partial Okounkov bodies. As a very more concrete example, let's consider the case of P1 and L is still O1 and nu is the order vanishing at the point 0. And we have already seen that the corresponding Okounkov body is given by the interval from 0 to 1. Now when we add a singular metric H to the picture, if we require that the singularity of H along the point 0 looks something like A times log Z squared, this is the simplest singularity, the log type singularity, then the partial Okounkov body is given by the closed interval from A to 1. So from this picture, you can see two things. First of all, the partial Okounkov body is always contained in the Okounkov body. It's a smaller part. And the second point is when A gets larger, that means when the singularity of H becomes worse, then the corresponding partial Okounkov body becomes smaller as well. And it turns out that this is true in general. The more singular the metric H is, the smaller our convex body becomes. This is a general phenomenon. What about the volumes? Recall that the volume of the Okounkov body is given by the volume of the line bundle, which by definition means asymptotically how many sections there are for L to the kth. We normalize it by k to the nth. And similarly, in the partial Okounkov body setting, we have a similar result. The volume of the partial Okounkov body is given by the asymptotic growth of the L2 sections of L. And again, this is a fairly non-trivial result. If we compare this, I read the formula again. If we compare these two formulas together, we see that when H has minimal singularities, then all sections are L2. And then in that case, the right-hand side of the theorem is the same as the right-hand side of the Euro volume. So that means they have exactly the same volume. And as I explained earlier, the partial Okounkov body is a smaller part in the Okounkov body. So when H has minimal singularities, they have exactly the same volume. So that means they are exactly the same object. As a corollary, when H has minimal singularities, the partial Okounkov body is equal to the Okounkov body. So in that sense, the partial Okounkov bodies, they are really some generalizations of Okounkov bodies. And it makes sense now to say that the theorem about the singularities, about the fact that the partial Okounkov bodies are universal invariants of the singularities of H, there are truly some generalizations of the classical results about the numerical classes of L. And on the other hand, we know that the Okounkov bodies of any line of all possible projective varieties and all possible line bundles, they only form a countable set. So there is no way to think about the corresponding continuity. But if we introduce the partial Okounkov bodies, we have some extra flexibilities. And it turns out that the partial Okounkov bodies, they are continuous with respect to the metric H. And here, of course, in order to talk about the continuity, we need to have a topology on the set of H, on the set of singular metrics. And it turns out that there is a very natural topology introduced by Darvas, Dines, and Lu in their papers. It's a topology comparing the differences between the singularities of two different metrics, two different singular metrics. And I will not talk about the details about this topology since it's rather technical. But anyway, the important thing is we really get a continuous function from the set of singular H to the set of convex bodies. So see that the convex bodies, these convex bodies can really move in a continuous manner within the set of convex bodies. So it's rather different from the behavior of the Euro Okounkov bodies. Apart from the definition I introduced above, there are actually two different but equivalent ways to define the partial Okounkov bodies. The first way is to consider the level size of level K in our object, gamma nu LH. We consider all points in level K, and we consider the corresponding convex hull. This is a subset of the level set of K, and we make a rescaling to make sure that it's a subset of level 1. So we will scale it by K to the -1. And you end up with some convex body on the level 1 subset of Rn plus 1. So this is a subset of Rn. When K tends to infinity, this object, this convex body, this polytope, converge to delta nu of LH. And this is a Hausdorff convergence. And this is a rather non-trivial result. And in general, the same thing fails for a general almost semigroup. But for this very particular almost semigroup, this is true. And the second point of view is to regard the delta nu as a Hausdorff limit of a net. And the net is given by considering all variational models of x, say pi from y to x, and we pull back our L and minus the divisorial parts of the singularity of H. And in that way, we end up with some object lying in the Nihonsabedi group. We can consider the corresponding Euro Okounkov body delta nu. And if we take the corresponding Hausdorff limit, it differs from our partial Okounkov body only by some constant vector characterized by the singularity of H, which is something which I denote by nu H here. I will not go very deep into these two different point of views, but at least this point of view shows that the partial Okounkov bodies, they are really something natural from whatever kind of point of views. And also the second point of view allows us to generalize the partial Okounkov bodies to other base fields instead of only C. Although the partial Okounkov bodies, the general definition was written down only 3 years ago in my paper, but there are a few special cases already widely known in the literature. For example, in the toric case, this is already something widely studied in the literature. Let's suppose that everything here is toric, like our variety, our line model, the singular metric, and the flag. Everything are supposed to be toric invariant. And in that case, it's very, very well known that the singular metric can be identified with the convex function from the corresponding co-character lattice tensor R to R. NR is something like R to the nth. It's a co-character lattice. And in the toric setting, the partial Okounkov body can be identified with the gradient image of H. That means we take the gradient, H is a convex function, we can take its gradient image, and we take the closure, we get a convex body in the character lattice. And this convex body is sometimes known as the Newton body of the metric H, and it has been widely studied in the literature. Yeah, and there are also several other cases where the partial Okounkov bodies are essentially known, like in the case of filtered linear series, but I'll mention it a bit later on. Finally, something more exciting. Let's talk about some applications of these Okounkov bodies. There are applications in the theory of Okounkov bodies and also applications in other fields. And it's pretty exciting that these seemingly arbitrary objects like these partial Okounkov bodies could find tremendous applications in different fields. The first result is about the slicing of Okounkov bodies. There are two different theorems proved in this direction. The first result is about the slicing of the Euro Okounkov body. Suppose that L is a baseline model, then after under some very mild assumptions, and we also consider a flag on our manifold X, say Y1 to Yn, and then under some very mild assumptions, the intersection between delta L and the intersection and the parts where X1 to Xk are equal to 0. They are given by partial Okounkov bodies of some objects, and the object is the recently defined object called trace operator, defined in the joint paper by Tamas Darvas and myself. But anyway, the point is, even if we are only interested in the Okounkov bodies, we want to understand its slicing, its intersection with the coordinate axis, then we have to consider the partial Okounkov bodies. And unfortunately, it turns out that this result contradicts some widespread results in the literature, like in the paper by Choi Park Wong, where they claim that the corresponding intersection is given by the Okounkov body of the restriction of L, but which turned out to be wrong. Another example of the slicing of the Okounkov bodies was proved by Kaveh Zhang around 1 year ago. The first result only considers the boundary slice, but the second result by Kaveh considers the interior slice. So we considered our delta L, and we consider the slice where x1 is equal to t, and where t does not take the two extreme values, because in general delta L is a convex body. You can imagine like there are two extreme values where the intersection there are two extreme values of x1 on this convex body, and we're taking x1 different from the minimal value of x1 and different from the maximum value of x1. And in that case, the slice, the intersection delta L and x1 equals t is given by a partial Okounkov body. And this result was first observed by Kaveh Zhang and using a very deep extension theorem about Kähler currents. And this observation actually played a key role in our proof of the volume identity of the transcendental Okounkov body as well. And that was a result by Tamas Darvas, Hemi Khaboulet, David Binistrom, myself, and Kaveh Zhang 1 year ago. In general, this is what the picture is like. We consider, even if initially we are only considering the Okounkov body delta L, if we take the slice at x1 equals 0, this is a partial Okounkov body. If we take the slice at x1 equals the middle value, this is still a partial Okounkov body. The only place where the result is not known is when at the rightmost extreme points. At that point, we don't know if the intersection is a partial Okounkov body or not. And in general, modulo some technical hypotheses, technical conjectures, we expect that in the same picture holds for partial Okounkov bodies as well. If we begin with the partial Okounkov body, we take the slices, apart from the extremal cases, we expect that the slices are partial Okounkov bodies. And I have a proof of that modulo some very deep conjectures about the extensions of Kähler currents. And another very important application is in understanding the Lelong numbers. Suppose that our evaluation is induced by a flag, say from Y1 to Yn. Then the position where our convex body is in the space is related to the Lelong numbers. And here is the result proved in my paper as well. The minimum of x1 along our convex body, xy means the first component of x. So it's like the x in the picture is the distance of the dotted line. That one is equal to the generic Lelong number of our singular metric along y1. That means the minimum of the Lelong number of h along y1 is an intrinsic characterization of the singularity of h along y1. So in terms of the picture, it seems very clear already. The blue line, the distance, the length of the blue line is the generic Lulong number. Why is it useful? Let's talk about corollary recently observed by Yi Yao in a toric setting, whereas the previous theorem holds for in general for any variety, but now let's only consider the toric setting where we can state the corollary in the most convenient way. Even in that case, this result seems to be new as well. We consider two different prime divisors, toric invariant, of course, D1 and D2. Then the Lulong number, generic Lulong number of H along the intersection of D1 and D2 is bigger than the sum of the generic Lulong number of along D1 plus the generic Lulong number along D2. This seems to be a rather strong inequality. And if you look at in the picture, it's something very simple. You consider the following picture where the outer part, sorry, this should be theta instead of nu. The outer part is the Okounkov body of L, and the inner part is the partial Okounkov body of L and H. And the distance between this guy and the boundary, let's say the leftmost edge correspond to the divisor D1, and the lower edge correspond to the divisor D2. Then the distance from the convex body to this boundary line correspond to the generic Lulong number of H along D1, as shown in the previous theorem, and the Lulong number along D2 is given by the length of the dotted line from the partial Okounkov body to the lower edge, and the left-hand side, similarly by taking the toric blow-up, is given by the distance between the intersection point of these two edges. That is the corner point. The distance between the corner point to the partial Okounkov body. The length of this dotted line is the left-hand side. So eventually, it's very simple to show that the distance between this point to the convex body has to be bigger than the distance between these two guys. The sum of these two lengths is a very simple convex geometry. Of course, this result can also be proved if you are familiar with the Archimedean point of view. It's simply given by the locally convexness of the corresponding Archimedean potential. But from the Archimedean point of view, you can only get the inequality itself. But from the partial Okounkov body point of view, it gives you more, because it gives you the precise relation between the left-hand side and the right-hand side. It tells you how to view the difference between the left-hand side and the right-hand side geometrically. And this observation was recently made by Yi Yao. And of course, the same result can be generalized to like many more prime divisors, parabolically different. You always have the same thing. And final application is in the construction of the so-called dystomotic errors. If you are working on K-stability, you should know that there are dystomotic errors associated with the test configurations constructed in the complicated way. And the test configurations they admit completion, a metric completion. And their completion is given by the so-called Archimedean matrix on finite energy Archimedean matrix on the Berkovich analytification of the line bundle. But anyway, in general, there is an Archimedean corresponding theory, an Archimedean pre-potential theory developed by Buxton and Johnson. And in their theory, an Archimedean metric is something generalizing the notion of a test configuration. Using the theory of partial Okounkov bodies, we can prove that an Archimedean metric in the sense of Buxton-Johnson induces a canonical error on R. And when the Archimedean pre-subharmonic function comes from a test configuration, this construction extends the classical construction for test configurations. And the interesting point of the statement is that it's completely independent of the Okounkov bodies, but it turns out that the proof has to depend on the Okounkov bodies. Last month when I was in Cambridge, I talked with A.G. Inoue, who also carried out a very similar construction, but only when L is an ample line bundle. But in our case, the L can be very general. It can be any pseudo-effective line bundle. And the proof consists of 3 steps, and you can see where the Okounkov bodies come from. The first step is due to the theory developed by Tamas Darvas, myself, and Kaveh Zhang. We show that the Hermitian matrix can be identified with concave curves of matrix. Here by matrix, I mean a matrix on the line bundles in the complex setting, in Euro complex setting. Tau is a real variable, and phi tau is a metric on the corresponding line bundle. And then the next step is to choose a valuation or a flag and construct a corresponding concave curve of convex bodies. So we pass from the curve of matrix to the curve of convex bodies. These are the partial Okounkov bodies. And these guys, they're a concave curve of convex bodies. And from a concave curve of Okounkov bodies, there is a canonical way to construct a random error on R. And that was already contained in the Buxton-Chen paper, which is already very well known. And in particular, we can show that the family of Okounkov bodies constructed from a filtered linear series, as in Buxton-Chen's paper, they are all partial Okounkov bodies. There are special cases of partial Okounkov bodies along the way. And the construction, as you can see from the construction, it seems a bit arbitrary because it depends on the choice of evaluation. So it's very hard to say if the result mirror is canonical or not. But it turns out that this is true. We can prove that the result random error on R, the Duster-Hickman error, does not depend on any choices. It's really a canonical error. Finally, I want to mention that almost everything I explained in this talk can be extended to the transcendental setting. That means we don't begin with the line bundle, but we begin with a corresponding big 1-1 cohomology class, which is not necessarily in the Nehong-Sabedi group. And in that case, we can still construct everything. And this is a kind of non-trivial. And the first step about the transcendental Okounkov bodies was carried out by Darvas, Heboulet, Whitney Strom, Zhang, and myself in the paper of last year. And the second step of extending the partial Okounkov bodies is carried out in my lecture notes in Zhejiang University, the reference to which you can download from my homepage already. And on this final page, I want to propose 2 conjectures, which are always of interest to me. If you are an expert, you could easily understand the first part of the conjecture, because here I need the notion of eigenvalue singularities. But if you are not an expert, let's only focus on the second conjecture, which is a special case of the first one. Assume that L1 to Ln, there are big line bundles on our variety X. Then the conjecture is that the movable intersection number from L1 to Ln is given by the supremum of the mixed volumes of the corresponding Okounkov bodies, where the supremum runs over all possible flags or all possible valuations. And the conjecture seems to be reasonable because recorded by the theorem of Zhou, the Okounkov bodies, there are universal invariants of the universal numerical invariants of our line bundle. But we also know that the movable intersection number depends only on the numerical class of these line bundles. So in principle, there should be one way to reconstruct the movable intersection number from these Okounkov bodies. And the naive guess is that the movable intersection number is equal to the mixed volumes of these convex bodies, which turns out to be wrong. So my conjecture is that if we consider all valuations and we take the soup of the corresponding mixed volume, we end up with exactly the same number as the movable intersection number. And if you have any ideas about this conjecture, please let me know. And I'll stop here. Thank you.